Hello and welcome to this video on the Dzhanibekov effect. This is also much more easily called the tennis racket theorem or the intermediate axis theorem. That all sounds fancy and technical, but what does it mean? In short, a rigid structure, like a tennis racket, has three axes of rotation, but two of these are relatively static while the third is not. That means that the rigid object will rotate on only one axis. The common example for this is when a tennis racket is thrown in a way that the handle rotates away from the body and then back towards the body. The face of the racket will also make a half turn in the process of, rotating. The key thing here is that any rigid object has three main axes of rotation: left, right, up, down, backwards and forwards. This should be fairly obvious. It's your three standard dimensions. This means that there are three distinct and different ways in which something can spin or rotate. This thing or object will only be stable on only one axis or near one axis, but there are three. So what about number two? Well, this is where the key thing is. The second axis will be unstable, and this is known as the intermediate axis, while you have the third axis, that is the one that is the actual rotation, that is the major turning point. That's why the racket makes a half turn on its face, but a full 360-degree turn on the other that actually rotates. It's a rather bizarre looking effect, and it's only ever really observed when the body or the thing is rotated on an axis that's near the intermediate axis. So in the case of a tennis racket, because you have the lengthwise, the up-down motion that rotates, you have the left-right rotation, and you have the back and forwards rotation. This takes advantage of two of these in a manner of speaking. Application-wise, it's a little more bizarre and somewhat more difficult, let's say. And that's because we're going to drag in mathematics, which for some people might be triggering a very unpleasant response right now. The maths involved is Euler's equations of motion, and these are all related to inertia and time. It's also an interesting application of Euler's equations. What we will summarize it as understand it can get a little more complicated than you might want to handle, is that each of the axes is spaced, and so you have 1, 2, and 3. So long as you have axes 1 and 3 being more stable than they are for axes 2 will move because it is close to number 3, and number 3 is what you're going to be seeing move. This is why we get that half turn as mentioned, the intermediate axes. With this knowledge, the question becomes quite simple and should have had people screaming at their screen for quite some time. What's the point? The first use that comes to mind is astronomy, the movement and rotation of planets, especially if they have an irregular shape for the whole planet, or importantly in some cases if the core has an irregular shape. The reason for this is that if you can observe a relatively, if not nearly perfectly spherical planet, yet its orbit is not quite spherical, it's possible to argue that the core inside is not a spherical shape, and it means that you could either have something, say, like liquid water that gets pulled by gravity of the sun it orbits, or you might have a solid core in the center of the planet that, for whatever reason, is irregularly shaped. We also have equations around motion. Remembering what we said about there being three axes and that Euler's equation that's applied here has, let's say, application there too, trying to avoid the technicalities to make people frustrated and disappointed. So long as you have that intermediate axis that causes a change, you get this bizarre phenomena. And we've seen this in applications in engineering to be specific. Explorer 1 is a great example. It's a satellite and spacecraft that was intended to be launched by the United States of America in 1958 and designed to only spin along its longest axes. This would generate the least possible inertia, which is what you want if you're sending something well into space. The problem is that's not what it did. Instead, because of the way it was designed, it instead started to turn in the wrong way and basically almost tumble. What it identified, and the major flaw in a lot of the things that are using this, is that if your structure is not perfectly rigid, what you end up getting is energy dissipating from various elements that aren't rigid. These are called flexible structural elements. and those flexible structural elements will then cause it to not follow the rules, such as having that one full turn and one half turn on each of the three axes. It's also arguably a case of why phones and toast always fall on the side you do not want on the floor, and similar. The overall concept here can be summarized as when something is not exactly rigid, but it can flex and bend, or in other cases it contains liquid as with a molten core, what you get is a certain amount of freedom in whatever body is moving, and this causes the dissipation of the energy that would otherwise go into that rotation. Because of this, the energy decreases and therefore you don't get that rotation in the same manner, or at least it will keep releasing that energy until it gets to a point of stability. This is important because if you don't have that stability, you'll keep getting movement, and that movement will then have to deal with inertia, because inertia is always a pain. Things that stay in motion will remain in motion until an outside force acts, and conversely, things not in motion will not go into motion until something acts on them. If you were to qualify this, you can see three things that are the premise of everything. Something will rotate around its second major axis for a short time. It will undergo a motion on its second major axis that causes it to reverse, and it will do so again and keep repeating doing so until something stops it or it runs out of energy. You can see this in a video demonstrating all kinds of things in space where they will tumble around for a while, but the way they tumble isn't exactly the same in all respects. Different shapes, and particularly things with different ranges of motion, will move differently. Things that have three irregular directions, so for example, your basic phone. It's a rectangular shape with a slight thickness. Because of this, it will tumble along its long edges, it will rotate slightly on its width edges, but the actual third dimension won't really shift at all. This is also why the theory, while being known for over 150 years, is still not exactly in use. We know what it is, how it works, but not necessarily what to do with it just yet, or at least we've not yet been able to apply it successfully, and that's perhaps the key. A successful application rather than just knowing what something is. It's a perfect example of the axiom of the difference between wisdom and knowledge, involving tomatoes and fruit salad. Thank you for watching this video. If you found it interesting, consider liking, sharing, and subscribing. Please do post any comments, questions, or suggestions you have below.